Welcome to another episode from the Veterinary Medicine Digest. Today, we are embarking on an extensive exploration into one of the most perplexing neurological conditions encountered in ruminant practice, known as Polioencephalomalacia, and a truly extraordinary clinical occurrence where this metabolic brain disaster crossed paths with a rare surgical emergency of the gallbladder. Polioencephalomalacia, which is often referred to as cerebrocortical necrosis, stands as a metabolic disease that results in profound neurological disturbances. While this condition can strike goats and sheep of nearly any age, it is the younger animals that seem most frequently targeted by its devastating effects. When we look at the core of what causes this breakdown of the brain's gray matter, we find that scientists have pointed to two primary culprits: a critical deficiency in thiamine, also known as vitamin B1, or an intake of sulfur that far exceeds what the body can safely process. To truly understand polioencephalomalacia, we must first appreciate the delicate balance of the ruminant's internal ecosystem. For a long time, the veterinary community attributed this disease almost exclusively to thiamine deficiency. Under normal conditions, thiamine is an essential nutrient that is actually produced by the ruminal microbiota in amounts that usually meet the animal's requirements. However, this safety net does not exist for young ruminants that haven't yet developed a fully functional rumen. They remain entirely dependent on getting enough thiamine through their diet. When thiamine is available, it plays a vital role in the very engine of life, acting as a cofactor for enzymes like pyruvate dehydrogenase and alpha-ketoglutarate dehydrogenase, which are necessary for cellular energy metabolism. But what happens when this system breaks down? The most significant factor that can sabotage the production of thiamine by the ruminal microbiota is a condition called ruminal lactic acidosis. This often occurs when animals consume diets that are too high in grain or rich in carbohydrates. This shift in diet drops the pH of the rumen, which unfortunately kills off the beneficial thiamine-producing bacteria and allows a different group of bacteria to flourish, those that produce an enzyme called thiaminase. These thiaminase-producing bacteria, including species like Clostridium sporogenes, Bacillus anurinalyticus, and Bacillus thiaminolyticus, act like metabolic vandals, actively destroying the thiamine before the animal can use it. Interestingly, the environment itself can provide sources of these destructive enzymes. There are certain plants that naturally contain thiaminase, such as the bracken fern, horsetail, nardu fern, and prostrate pigweed. Even things as unexpected as consuming carcass fragments that contain thiaminase-producing Clostridia have been linked to thiamine deficiency in cattle. Beyond natural sources, the medical treatments we provide can sometimes backfire. Medications used to fight parasites, such as amprolium, sulfonamides, and trimethoprim, are suspected of causing polioencephalomalacia because they act as thiamine antagonists. These compounds essentially block the transporters in the intestines that allow thiamine to be absorbed into the bloodstream. The consequences for the brain are catastrophic. When thiamine is scarce, the energy metabolism of neurons is compromised. The brain is a high-energy organ, and without enough thiamine to power the pentose phosphate pathway, energy production in nervous tissue falters. This deficiency also slows down the synthesis of essential neurotransmitters and triggers a cascade of cellular stress, leading to neuronal degeneration and death. While thiamine deficiency was the traditional explanation, modern veterinary science now attributes many cases of polioencephalomalacia to excessive sulfur intake. Animals can be exposed to dangerous levels of sulfur through a variety of dietary ingredients, including molasses, gypsum, and even certain byproducts of the ethanol industry like distillers' grains. Even the water they drink can contain toxic levels of sulfur. While beef cattle can tolerate up to 0.39% of dietary sulfur, the exact limit for goats remains a mystery. The biological pathway of sulfur toxicity is a dark reflection of normal metabolism. Usually, sulfates in the rumen are converted into sulfide ions to help build amino acids like methionine and cysteine. But when sulfur levels are too high and the ruminal pH drops, these ions form hydrogen sulfide gas. This gas is either absorbed through the rumen wall or inhaled back into the lungs after the animal eructates. Once this gas hits the bloodstream, it can overwhelm the liver's ability to detoxify it. When hydrogen sulfide reaches the central nervous system, it behaves like a cellular poison, inhibiting cytochrome C oxidase and effectively choking the cell's ability to produce energy through oxidative phosphorylation. When we observe an animal suffering from polioencephalomalacia, the clinical signs can be quite variable, but they are always dramatic. It might start with something subtle like apathy, a lack of appetite, or an animal simply separating itself from the flock. In cases caused by sulfur, the gas the animal burps up might even smell like rotten eggs. As the neurological damage progresses, the signs become unmistakable. The animal may stagger, circle, or press its head against a wall. One of the most classic signs is known as stargazing, where the animal lifts its head and neck upward as if staring at the sky. They often appear blind, with pupils that are fixed and dilated. In the final, most severe stages, animals experience muscle tremors, convulsions, and a rigid posture with the head drawn back, a condition known as opisthotonos. Without rapid intervention, death usually follows within 1 to 3 days. Diagnosing this condition often requires a high degree of clinical suspicion. Veterinarians look for the classic signs of blindness and convulsions, and a positive response to thiamine treatment can be a strong indicator. At necropsy, a definitive sign of polioencephalomalacia is the presence of autofluorescence in the cerebral cortex when examined under ultraviolet light. This glowing of the brain tissue is a hallmark of the necrosis and biochemical changes occurring in the gray matter. This brings us to a fascinating case study that highlights how polioencephalomalacia can present in ways we we never expected. Imagine a 10-year-old purebred Hampshire Down ram that was suddenly struck with acute neurological signs. This ram was initially just uncomfortable and had a spastic gait, making it unable to keep up with the rest of its herd. Despite being treated with antibiotics and analgesics, its condition spiraled downward. It began vocalizing, having convulsions, and making involuntary bicycling movements with its limbs. When a postmortem examination was performed, the veterinarians found the expected signs of polioencephalomalacia. The brain was swollen, showed yellow discoloration, and glowed under ultraviolet light. Histological examination confirmed the laminar neuronal necrosis typical of the disease. However, when they opened the abdomen, they found something virtually unheard of in small ruminants. The ram's gallbladder was markedly enlarged and had undergone a complete clockwise torsion about its long axis. This torsion had caused severe circulatory disturbances, leading to a thickened gallbladder wall filled with blood and bile, a state of coagulative necrosis. This was a primary torsion, meaning there was no other displacement in the abdomen that caused it. To understand the rarity of this, we must look at other species. In humans, gallbladder torsion is a rare disease that mostly affects elderly women, often linked to anatomical variations like an elongated mesentery that allows the gallbladder to swing and twist. In domestic animals, secondary cases have been seen in dogs and cats as a complication of stomach twists, and in dairy cattle it has been associated with a specific type of intestinal twist called a duodenal sigmoid flexure volvulus. This brings us to a critical question: was there a link between the brain disease and the gallbladder twist in this ram, or was it just a whisk of fate? One theory suggests that the neurological damage of polioencephalomalacia could have altered the ram's gastrointestinal motility, leading to the stasis of bile and increasing the risk of the gallbladder twisting. Another possibility is that the metabolic crisis caused poor tissue perfusion and hypoxia, which might have triggered the torsion if the gallbladder was already slightly displaced. While a direct causal link hasn't been proven, the simultaneous occurrence of these two conditions is a powerful reminder of how interconnected the body's systems truly are. To put this gallbladder finding into perspective, we can look at what we know about biliary disease in other species. In cats, for instance, diseases of the biliary system are relatively uncommon, but can be quite serious. Cats can suffer from biliary obstruction due to things like inflammation of the liver and bile ducts, stones, or even traumatic avulsions of the common bile duct. A case series of 4 cats illustrates how complex these issues can be. One 6-year-old cat presented with jaundice and lethargy and was found to have a necrotic gallbladder with a tear in it, along with stones. Another 2-year-old cat suffered a common bile duct avulsion after a road accident. What's striking about feline biliary surgery is the high mortality rate, particularly when the bile has to be surgically diverted into the intestines. Only about 50% of cats survive more than 2 weeks after such diversion procedures, and many struggle with intermittent vomiting and appetite loss for the rest of their lives. These feline cases show that even with advanced surgical techniques, the biliary system is unforgiving. When we look at cattle, the story of the gallbladder often intersects with the unique anatomy of their intestines. Ruminants have a very long and mobile duodenum. Recently, a new condition has been recognized in dairy cattle called duodenal sigmoid flexure volvulus. In these cases, a part of the duodenum twists, and because the common bile duct is often involved in that twist, it causes a mechanical obstruction of the gallbladder. This leads to the gallbladder becoming engorged, a change that veterinarians can actually see using ultrasonography. These cows often show severe electrolyte imbalances and high levels of bilirubin in their blood, mirroring some of the systemic stress we see in polioencephalomalacia. The theme of oxygen deprivation and its effect on the brain is also echoed in other species, such as horses. A case study of a cloned American quarter horse foal describes how it developed hypoxic or ischemic encephalopathy. This foal was born with signs of neonatal maladjustment syndrome, which is believed to result from a lack of blood flow or oxygen to the brain during or before birth. Much like the ruminants with polioencephalomalacia, this foal's brain showed yellow discoloration and the same apple-green autofluorescence under ultraviolet light. The microscopic damage, laminar cortical necrosis, was nearly identical. This comparative pathology highlights that whether it is caused by a metabolic toxin like sulfur or a lack of oxygen during birth, the brain's response to extreme stress often follows a similar, tragic path. If an animal is fortunate enough to survive the acute phase of polioencephalomalacia, what does the future hold? A study conducted on sheep used a medication called amprolium to induce the disease and then treated them with thiamine to see how their brains healed over 6 months. The results were surprising. In the animals that died acutely, the brain was swollen and showed clear signs of neuronal death and edema. But in the sheep that recovered, some through treatment and one even spontaneously, they appeared clinically normal for half a year. However, when their brains were examined after 6 months, there were permanent, visible changes. There were quasi-empty spaces or cavitations in the brain where the gray matter had simply vanished. These areas were now occupied only by blood vessels and scavenger cells known as Gitter cells, which had moved in to clean up the dead tissue. The fact that these sheep could function normally despite losing significant portions of their cerebral cortex is a testament to the resilience of the nervous system. It suggests that as long as the brain stem remains intact, an animal might be able to compensate for extensive damage to the higher centers of the brain. This journey through the science of polioencephalomalacia and its rare association with gallbladder torsion teaches us several vital lessons. First, we must be vigilant about the diets we provide to our ruminant friends. Adapting them slowly to high-grain diets and carefully monitoring sulfur levels in both feed and water can prevent the metabolic storm that leads to brain necrosis. Second, the stargazing animal, or the one that suddenly goes blind, is a medical emergency that requires immediate action, often in the form of high-dose intravenous thiamine and supportive care to reduce brain swelling. Third, we must remember that the clinical picture is not always straightforward. The case of the ram reminds us that even when a diagnosis seems clear, like the classic signs of polioencephalomalacia, there may be other silent, rare emergencies like gallbladder torsion lurking in the background. The acute abdominal pain of a gallbladder twist could easily be masked by the dramatic neurological signs of a failing brain. Finally, our understanding of these diseases is constantly evolving. Whether it is a new condition like the duodenal twist in dairy cattle or a rare twist of fate in a Hampshire ram, every case contributes to a larger map of veterinary knowledge. By studying these connections between the rumen and the brain, between the bile ducts and the nervous system, we become better equipped to protect the health and welfare of the animals in our care. Thank you for listening. The titles for the reference papers are in the video description. From VetMed Digest, where we keep minds inspired, hearts light, and tails wagging.